Welcome back. Today we're going to discuss fatigue, and you have a couple of things you need to be sure you know today. We're going to go over the basic approaches to fatigue characterization, and we want to focus a little bit on the assumptions that underlie those, and you need to pick those up. And then we're going to identify or define the fatigue limit, fatigue strength, fatigue life. I'll show you what an SN curve looks like. We're going to introduce DAD and delta K curves, and we'll do some work with those in class. So, to set us in context here, most engineering failures are caused by one of four things: fatigue, corrosion, wear, and nosy politicians. Fatigue failures, obviously we're going to talk about today. We will discuss creep in the next session, and we'll also talk about wear at that point. And then corrosion is the last topic that we'll be covering this semester, so you're going to get the three horsemen that you have control of. And the other thing you'll notice about these, corrosion and wear are surface phenomena, and it turns out most fatigue failures actually begin on the surface. So these are all going to be very surface-dependent processes, and they're responsible for the vast majority, 90+% of all failures of engineered systems. So what is fatigue? It's simply a cyclic load or strain. That means we apply it, we remove it, apply it, remove it. Or you may have loads varying from one positive value to another. The key is it's a changing load, changing in time, usually at fairly regular, fairly high frequency, so that we're piling up lots and lots of cycles. And the result is usually a failure process that takes some time, often can take millions of cycles, years to happen, or to lead to failure. Although there are some cases where that time can be fairly short, obviously. So there's two types of fatigue. We'll categorize it as high cycle fatigue, where the stress stays below the yield strength, at least globally. So macroscopically, it's going to be a brittle fracture. You're not going to see any evidence of yielding. And we may be talking about very long lifetimes, as I said, on the order of millions of cycles. Low cycle fatigue, on the other hand, is fatigue that occurs when you've had the global stress exceeds the yield strength of the material. Usually it's not very many cycles to failure. It's going to be obvious that yielding has occurred. And if you break a coat hanger by bending it back and forth, which we'll do in class, that's a low cycle fatigue failure, just not very many cycles. Now, terminologically, we need a couple of terms here. Your stress is going to be varying with time, ideally sinusoidally, but in reality it's going to be all over the place. There'll be interesting load histories. But you're going to describe that load variation with a minimum stress and a max. That's the minimum and maximum applied. The range of the stress is the difference between the min and the max. And the amplitude is simply defined as half of the range. Okay. So those are basic definitions, and we'll be using those as we look at graphs and so on. Now, as we approach the problem of fatigue, if you remember back to failure, just 2 lectures ago, we pointed out that there's 2 stages in any failure, that all components that break into 2 pieces, 2 or more pieces, have experienced crack growth. But cracks don't just appear. There's an initiation process, which is usually dominated by a particular set of mechanics issues. And then there is propagation, which is often controlled by different things than the initiation process. So when we design a structure, we can either approach it in a manner where we're going to try to prevent initiation of cracks, and we're going to attack the flaws and try to fix them so that they can't cause failure. We may either remove them, or we may do things to make them unable to cause failure. Or we may assume that we have flaws, we know what the flaws are like, either because we measure them or because we just know what tends to be made in that process. And we're going to use fracture mechanics to predict how that flaw is going to behave. And if the structure has a long lifetime and is at high risk of either loss of life or serious financial losses, then that structure may be measured or monitored periodically to track those flaws, see what's happening. And that's what we do with aircraft and pipelines and nuclear containment structures and other high-risk structures. We'll be inspecting them for the flaws. So let's look at the high cycle fatigue process. If we approach this with let's eliminate defects, approach. So we're going to assume a material that is essentially free of cracks, at least initially. What we find is that we get local yielding at defects or a stress concentration. These can be things like fillet roots on the surface, scratches. This could be inclusions, impurities, bubbles in the material, whatever. But those cause an elevated stress locally, which results in yielding right around that stress riser. Not globally. The rest of the section doesn't yield, so you don't see anything. If you're looking at the exterior or you're looking at the broken parts, you're not going to see significant plasticity. What happens is that local yielding causes dislocations. They pile up because it is a localized field. Eventually that field saturates and a crack forms. Once the crack takes off, essentially in high cycle fatigue, the period of the crack growth is not usually a big part of the life of the structure. If this has been our approach, we're not even going to worry about the crack propagation stage of life. Honestly, our goal is going to be to resist the initiation of cracks here. So how is this done? Well, the most common technique is to use an RR Moore fatigue machine, and it's a rotating beam machine. That is, this is the specimen, the material of interest. We have bearings here and bearings here. These bearings support, and then these bearings support a weight that's hanging, and this is a 4-point bed you think of as a vertical support here and here, and a downward force, 2 of them in the middle. And so this produces a uniform moment, or bending moment, across the center section, which means uniform stress, but the stress will be a maximum at the minimum section here in the center. And what happens is, because we rotate the specimen, but the weights always hang downward, the bending stress will be such that we'll have compression on the top and tension on the bottom. So if you look at a point on this beam, at the top it's in compression. As it rotates, as the motor turns it to the bottom, now it's in tension and it goes back. So we have fully reversing stress. The mean stress is 0 in this type of approach. And but we have full reversal, positive or negative on the top to positive on the bottom. This just runs until the sample breaks, and there's a counter over here that detects when this breaks. It stops the motor, and so there'll be a switch here that'll be triggered as this falls, and it opens the circuit, kills the power to the motor, so this doesn't keep spinning after it's broken, and the counter stops counting. You can hear it's usually a mechanical counter, it just goes click, 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 click. And we count the cycles of failure. And we're going to do that at different stress levels. So the initial plot, look up in the upper left here, we're going to apply different stresses, and we're going to count how many cycles to failure. That's the life in cycles of failure. And you just plot that, and you'll see a nice little curve developing here. And then suddenly we'll get to a stress level where nobody breaks. And nobody breaking is a problem. You run out here to this is 100 million cycles. That takes a long time. And so BCC and HCP metals have what is called an endurance limit. That is, there is stress level, in this case about 30 KSI, below which they will not fail by fatigue. So as long as the peak alternating stress stays below 30 KSI, you can load this cyclically forever and it will not fail. Above that stress, we have some variation. Now, this is a really terrible scale, obviously. So the first thing we do is you just take a log of the number of cycles to failure, and when you do that on a log scale, now it spreads this stuff out nicely, and then the 10 to the 8 here, that's our not broken, and our endurance limit again. Now, this is not a straight line, and we're materials engineers, so we're lazy, we like straight lines. So what we do is we go in and take another log, and so this is going to be log on this axis as well, on the strength axis. And then everything becomes nice and linear. We got linear data, and our endurance limit, this horizontal line. And in class, I'm going to show you how to construct an SN curve from simply the ultimate tensile strength of a ferrous material. Turns out this endurance limit is very well predicted by UTS. Anyway, so that's the SN curve as we normally use it. Endurance limit is the first parameter that goes into estimating the allowable stress in fatigue. And then we can modify the allowable stress to allow for surface finish and other things, but this is the stress below which you have infinite life. So you'll hear this called the endurance limit or the fatigue limit, and may even be called the fatigue strength, although that's not strictly true or accurate. Now, in FCC alloys, you notice I said we have an endurance limit in BCC and HCP alloys. We do not have an endurance limit in FCC alloys. The problem is they do not strain harden enough around defects, and they just keep, there is no stress below which you won't get yielding around defects and eventually form a crack. Now, it may take many, many, many cycles, so practically 10 to the 9th is almost infinite life in most applications. But that's, it's not a true infinite. And so this is the problem. We do not have a stress below which you have infinite life. Now, what we do with FCC alloys is we're going to specify a desired lifetime, and from that get an allowable stress. So if you tell me you need 1,000,000 cycles, we'd come up for 7075 aluminum, come up here, we'd read across and say, okay, looks like about 80 megapascals will give you 1,000,000 cycles to failure. And so that becomes your fatigue strength for this material for a desired life. You could also have, what's the applied stress, and they'll tell you what the design life is. So if we're at 140, we'd come across, and it's going to be about 10 to the 5th cycles, so 100,000 cycles. So you can either specify a stress and find a life, or specify a life and find the allowable stress. But you do not have an infinite life option in FCC materials. Now, we can then build SN curves for all kinds of different things. So this is one that is in your equation book you'll use on exams. This is for a 1040 steel. And there's two versions here. There's cast 1040 and wrought 1040. Cast means the molten metal is simply poured into a mold, and it's allowed to harden, and so that may have defects in it. It can have inclusions. The grain structure is can be fairly have defects built into it. Because of the casting process, you can have things called dendrites. And then a wrought material is a cast material that has been rolled or hammered or something into its final dimensions or final shape. And that forming process dramatically improves the properties. It tends to break up large inclusions. It's going to give you a controlled grain structure. And so wrought product is almost always superior. If you buy kitchen knives and you like really fancy kitchen knives, if you go look at the company's websites, there's always two grades of knives they sell. One is called a stamped blade, and they simply take sheet which has been rolled to some extent, but not heavily, and they cut out the blade from that sheet material and grind an edge, and it's just a stamped product. And then there's wrought product or forged product, where they take a bar that is larger than the blade, and they hammer it and they hammer it and they hammer it until it is the shape of the blade. It's going to be vastly superior. It will hold an edge better, but it's also usually 2 to 3 times more expensive than the stamped materials. So that's the extreme version of a wrought product, and it's been worked into its final configuration. So we see the wrought product is better, has a higher endurance limit than the cast product. But if we take our specimen and we notch it, that is, we scratch the surface with a file, both of the curves end up being pretty close. The wrought is slightly better, but they end up about the same because we've introduced the defect that's basically the same in both materials. And so the endurance limits are hardly distinguishable because we put a big notch in them. And so you see here the importance of surface finish and so on. Now, what's going to happen in design is that we're going to assume that our structure, whatever we're building, the metal in that structure is essentially the same as the metal in our test, as the samples in our test, that we haven't done anything to introduce new defects. If we have, there are ways to adjust the endurance limit, and there are fudge factors that you multiply by to reduce the allowable stress based on the kind of surface finish and all of those kinds of things. So the basic approach in the SN is we're going to assume flaw-free, and we're going to make sure that the specimens we test are as close to the structure that we're working with as possible, and if not, we're going to modify the strength, allowable stresses, to deal with that. And again, emphasize what we're talking about here is we're going to attack fatigue resistance with the SN approach by trying to prevent crack initiation. So we're going to try to interfere with the first steps that lead to crack formation. So if we look at what we might do to the material, think about hardness. If we strengthen the material, which would be reflected in the hardness, what happens to the endurance limit or the fatigue limit? Well, it turns out as we increase the hardness of the materials, in general we see an increase in the fatigue limit. Now we start seeing a lot of scatter out here, but that's at Rockwell C40. That's a fairly hard material. And most structural steels and so on are the steels used in automobile frames and so on are below Rockwell C40. So they're in this regime where we're looking at pretty much the linear relationship between the endurance limit and the hardness. If we look at ultimate tensile strength, this is data from a different source, we find that if we treat the fatigue limit as exactly half of the ultimate tensile strength, that would be this line continuing in a dashed line. So for moderate strength materials that have polished surfaces, we find that they pretty much follow, this is that region, they pretty much follow that 50% rule. And as you get to real high strengths, ultimate tensile strengths that are way up there, you don't see that. It starts to break down a little bit. The real materials are going to curve away. But this is pretty fantastic because it says if I know the ultimate tensile strength or I know the hardness, which lets me estimate ultimate tensile strength, the fatigue limit's about half of my UTS in both SI and US customary. Now if the specimens are notched, that doesn't work. And if they're corroded, that doesn't work. But for a normal, good surface finish material, you could start with a fatigue limit that's half of the ultimate tensile strength. Now, what are the limits of SN approach? Well, there's a lot of scatter. We saw that in the 70-75 curve. If you look here, very, very long error bars. And so if we're at 80 megapascals and I ask you what's the life, well, it could be just 1,000,000 cycles, and it could be about 500 million cycles. So a factor of 500, and so if you're talking airplanes, this is 10 years, and that's 5,000 years. That's a big range of lifetimes for a structure. So that scatter is really problematic in a lot of applications. It doesn't separate out initiation and propagation, and the propagation is part of the life we're measuring in the number of cycles to failure, but we don't know what that is. So there's a little less understanding of what's happening. We have a problem in that SN doesn't particularly work in low cycle fatigue because of the plastic deformation, and we don't have a good tool for that. And high cycle fatigue, obviously, it works reasonably well, but it doesn't handle the transition between these at all. So it's less than perfect, but it's fine for probably 80%, 90% of the engineering that you will do as a machine designer or as a structural engineer. But to look at another way we might approach this, let's talk about how cracks propagate. So we start in fatigue crack propagation. You have a closed crack. As a stress is applied, the crack opens. As the stress continues to rise, eventually the stresses right here at the tip exceed the yield strength and we begin to get plastic deformation. Remember, we calculated the size of a plastic zone, crack tip plastic zone, and so that's what this puppy is here. Now, this is cyclic loading, so we don't just load up once and make a plastic zone. We're going to unload this, so the structure is going to be unloaded. When that happens, all of the elastically deformed material around the crack that had stretched to allow the plastic deformation to occur, it's all going to recover. There's no more stress, so it all wants to go back to its original shape. The problem is that plastic zone is now distorted. This metal is changed shape, doesn't fit. And so we end up with a compressive stress that tends to close the crack, and it's going to distort this plastic field, and it's going to sharpen the crack. So we now have a sharp crack. It's advanced a little bit. The blunting causes a little bit of advancement, and then we sharpen the crack again. On the next cycle, we have a sharp crack. We get more blunting. Crack advances a little more, closes, it resharpens. So this is the fatigue crack propagation process. Now, interesting little tidbit. If you have a really large load that's applied, you're going to get a really big plastic zone. Remember, the equation from fracture was the plastic zone size is proportional to the square of the stress intensity divided by the yield strength. And we focused on the yield strength. As you increase the yield strength, you decrease the plastic zone size. But the flip side of that is if you apply a bigger K, that is a larger external stress, which results in a higher stress intensity, you get a bigger plastic zone. Now that means when you unload the sample, there's a lot more compression. If this is bigger, there's a whole lot more material that doesn't fit. You can get a really high compressive stress that's holding this crack closed. What happens then is if the next load cycle is a smaller load, it first has to overcome all of this compression before the crack can begin to open again. And so you may, in fact, stop a crack from growing by overloading it occasionally. That is, if you hot dog in your airplane once in a while, you may arrest a lot of the cracks that are growing in the structure and then extend the life of the airframe. So it's a little counterintuitive. And we're going to look at an application of that in a little bit. So how do we know this is the cycle, the process? Well, we can see it in the electron microscope, but we also have evidence on the surfaces of the broken parts. And so fatigue striations are the evidence of this cyclic crack growth process. And this is aluminum, and here's some polycarbonate from my PhD research that shows this, again, same kind of features, even though this is a polymer, very, very different mechanisms of yielding, but still the same kind of step growth. Now, macroscopically, that is with the naked eye, it is possible to see evidence of fatigue in what are called beach marks. And so you see there's this band of slightly different color. There's another band here. There's a band right here. All right, those are called beach marks because they kind of look like the lines that are left on the beach after the tide goes out. And those are visible to the naked eye. And they're not caused by these individual load steps or the individual cycles. They're caused by changes in the environment during crack growth. As the crack propagated, maybe the temperature changed or humidity changed or the loading direction changed a little bit. Any of those things will produce step changes in the surface appearance, and you can see those as beach marks. Now, what if we say, you know, we really would like to understand how these cracks are growing? So let's do a simple experiment. Let's just make a specimen that we can monitor the length of the crack in. So we're going to watch the crack grow as we cycle at different stresses. So sigma 1 is lower than sigma 2, or just the nominal stress level, and we're measuring crack length, A, versus number of cycles to failure. And so at a high stress, we see the crack grows rapidly, and at a low stress, the crack grows more slowly. And at every slope here, you could measure a velocity of the crack. How much is it growing per cycle, dAdn? All right. Well, this is a problem because every stress has its own curve, so I need to have a whole bunch of these curves for a given material so I could figure out what's happening at a given stress. That's not practical. So let's use the stress intensity factor to see if we can normalize the effect of stress in a growing crack. So remember that K is equal to the shape factor Y times sigma times the square root of pi A. Now, A is the crack length, sigma is the applied stress. What we're going to do is, this is cyclic loading, so you have a maximum stress and you have a minimum stress. So we're going to calculate the K value at the max and the K value at the min, subtract those, and call that delta K. All right. Now, if we run a test where we do not let delta K change, and the way you have to do this is, as the crack is growing, you have to change the loading, because as the crack grows, it is going to mess up and change the delta K. So if you adjust the load level, the stress level, so that delta K remains constant, we find that as the crack grows from its initial length, 30, to out here where we stopped it, somewhere, there's the edge of the specimen, so they didn't run all the way to the edge of the specimen, we have a constant slope. That is, the growth rate, okay, is constant. If you took a slope here, you'd have time per millimeter, okay, or flip that over, a millimeter per hour or whatever. So you take the reciprocal of the slope and you have a velocity of the crack, and that slope is constant for a constant delta K. All right, well, that's promising. That means that there's something fundamental. It doesn't matter how long the crack is, it will grow at the same speed as long as the delta K is the same. So it's delta K that drives the velocity. So a classic experiment then is to take a specimen where we can monitor the crack growth, and we're just going to track crack growth, and from that we calculate the velocity of the growth, and we usually will hold the stress constant, but because the crack is growing, the K is changing. So we'll plot the velocity of the growing crack versus the delta K, and usually do it on a log scale. Okay. Now, this is the startup problem, and it's not a big deal. There's not that much growth going on. The velocity is high, but the total growth is not that great. So this is a transitional region. We usually ignore region 1. And region 3, we're getting ready to go unstable. The crack is accelerating, and so you usually identify a critical level of delta K, which is dangerous. You don't want to move into zone 3. And that's going to give us what length of crack is the warning that we have to retire the structure or repair it, because if we keep going, we're going to move into zone 3. But in zone 2, we have a nice steady relationship between delta K and dAdN and the velocity of the crack. So if we fit a line to this, it will have a form of y log dAdN is equal to mx plus b. Okay, so n, x is log delta K. I'm going to call my slope is n. And then log of A is going to be my intercept. So there's an intercept, y-intercept out here someplace. Should be right there. If we take the inverse log of the linear equation, we get an expression for the velocity of the crack. dAdN is A delta K to the n. So n is the slope of this linear portion. A is the intercept, the y-intercept. And if you get those constants, then you have a formula for the velocity of the crack. And we're going to play with this in class and integrate it. You don't have calculus yet, most of you, so I'll do the integration for you to yield a formula that you can use to predict how long a structure is going to last. All right, let's talk about, well, here's real data for type 304 stainless, 316 stainless. They're very similar. And so this is the dA, here's your velocity, okay, in inches per cycle. And here's your delta K, which has the funky units of K, KSI root inches. And you see, there's none of the first region. Okay, so this is the region 2, which is linear, and then here it's going unstable. So we would probably identify this about 70 KSI root inches as the threshold K that we don't want to exceed, because we don't really want things to take off on us. The acceleration is becoming noticeable. Let's talk about a real application for some of these ideas. So if you think about these nice propane tanks, right? One of the great gifts to the griller, because you can go home after work and throw something on the barbie real quick. And you think about how these are used. They're a high-pressure vessel. They are loaded with an explosive gas. They're stored in garages and what have you. And when you do that, you get cyclic loading because of the temperature fluctuations in the garage. As it heats up, the pressure in the tank rises. As it cools down, the pressure drops. So the tank sees a cyclic load. And yet they're incredibly reliable. And there's really very little risk of having any failure of the tank. And in fact, they're so reliable that you don't usually buy a tank and then go get people to fill it and keep it. You now just take it to an exchange and turn it in, and they give you a filled tank, and somebody else gets your tank, and you got somebody else's tank, and whatever. And nobody's really worried about that scenario. So there's a hint about how it is possible to do this, and we're going to talk about this in class, but you may want to think about it. Can you imagine how we could use the facts that we've already talked about, overloads during fatigue that can slow the failure process, plastic zone size equation we use in fracture mechanics, okay, and how we might apply all of that to one of these tanks to produce that fantastically reliable and safe system out of actually a structure that's welded. This is a weld in the tank. All right, so next discussion will be on creep.